of Q&A that we are always having. There's a Q&A on the bottom of the Zoom, so you can ask your questions in writing, and we will then decide whether we want to interrupt and ask a few questions during the talk, and then in the end we will collect all the questions that you have asked to ask for the discussion. Let me see if it stabilizes. Okay, seems to be we're reaching the peak. Welcome to today's 1W-MINDS seminar. Speaker today is Gitta Kutyniok. Just a few words about her vita. She did her PhD in Paderborn and then the habilitation in Gießen. That sounds very German, but in fact it was not, because this included many positions at very different universities in North America in particular, then followed by a Heisenberg Fellowship that led her to the full professorship in Osnabrück, and then to TU Berlin, where she's still now. In addition, I think starting last year, she has an adjunct professorship of machine learning at the University of Tromsø in Norway. There's many awards that are listed. I can not name them all, but maybe most prominently, she's a SIAM Fellow. She is a member of the Berlin-Brandenburg Academy of Sciences and the Humanities. And next year, she will be one of the plenary speakers at the European Congress of Mathematics. Her research has spread many different fields over the years. So she has, I think many of you will know her work on shearlets, her contributions to contrast sensing, and also what she will be telling us today, namely her work in the area of data science, in particular deep learning. Maybe something that not so many people know is that Gitta is also an excellent teacher. She has been awarded, for example, a prize at the University of Paderborn, the Weierstrass Prize for Excellent Teaching. So without further ado, we welcome Gitta, and we're looking forward to your talk.
Yeah, thank you very much, Felix, for the very nice introduction. And I would also like to thank you and the whole organization team for the invitation. It's a great pleasure and honor for me to give a talk in this 1W-MINDS seminar series. Now, I think we all know how tremendously successful deep neural networks are in public life and also in sciences. But at the same time, we also know that there is a missing theoretical foundation. So we don't fully understand why they actually operate that well. And there are various directions people are going right now to delve more into the theory and understand it. And in this talk, I would like to show you a glimpse in certain directions, also what we did. I think, as you know, deep learning and artificial intelligence is around us, and certainly the presence will much more increase in the future. Just think of self-driving cars, think of surveillance tasks, think of legal issues. So for instance, in the States, I became aware that sometimes job applications are already pre-screened by neural networks, or the whole healthcare sector, where, for instance, in imaging modalities, deep learning is already used, but also to reach critical decisions. But as I said, at the same time, there are not enough theoretical results to actually really explain their success, which is also a problem in sensitive applications like, for instance, healthcare. And this is a problem which I think a lot of people are aware of. And let me just say there was an interesting incident. Basically, just 2 years ago, there was a conference on AI, and a plenary speaker, Ali Rahimi, he gave a talk. And he said machine learning algorithms in which computers learn through trial and error have become a form of alchemy. Researchers, he said, do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one AI architecture over another. And so this raised a vivid discussion. And I think in this whole regime, what I very much like is actually what Stephen Hawking said, because he said the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. And I think in this area, this is something which is really important, since sensitive applications are dealt with. We have to ask ourselves each time, do we actually know enough of these methodologies to actually apply it already to sensitive applications, and what do we actually need to know to be able to do that safely? Okay, so let's start delving a bit more into the mathematics of deep learning and deep neural networks, because these are actually really mathematical objects. So if you haven't seen this, what is a neural network? It is basically a function from, let's say, RD to RNL, where NL is typically chosen equal to 1, for instance, if you do classification. And it's a highly structured function. You see how it's composed. So these T's, these are affine linear maps, so AX plus B. And to bring in some nonlinearity into the game, this rho is applied. It's so-called activation function. It's, as I said, a nonlinear function, a univariate function, and it's applied component-wise. Then another affine linear map is applied, then another activation function, and so on. And so the number of affine linear maps is what we say here, capital L, the number of layers. So how does this connect to usually the graphs which neural networks are depicted as? Now here, in this case, I have as input dimension 4, so I have here x1, x2, x3, x4. Then these connections mimic the first affine linear map. I will go into a bit more detail on the next slide. Then in these neurons, I apply the activation functions, and then I keep going. So the next affine linear map and the next activation function, and so on. So now you also see that the number of layers here coincides with the number of affine linear maps. So let's go in a bit more detail how these connections arise. So let's make an example. Let's say the first affine linear map maps from R3 to R3. So we have our 3 components of the first input vector. And you see the first component of the output is a linear combination of these 2 weights times x2 and x1 and x2. So this is depicted by these connections. Then the second component of the output is this weight times x3, which is this connection. And the last is this weight times again x3, which is this connection. Then this, what's called the bias, is applied component-wise here in these neurons, and also the activation function. And then we keep going. So for instance, the next affine linear map maps from R3 to R2. Okay, so for instance, if you want to have a sparsely connected neural network, then you need matrices which have, so sparse matrices which have a lot of 0 entries. So what do you do now with a neural network? Well, you have a complicated function in the background, which is maybe defined on a lower dimensional manifold, and maybe it's a classification function. So think, for instance, you have some manifold, maybe in one area you have images of cats, in the other area you have images of dogs. So in computer science, people like always to distinguish cats from dogs. And let's assume the function outputs here the value 1 and here the value 2, so for classification. But now what you have at hand are just sample values. So some of these images with the correct labels. And now the task is from these to predict F. So now if you want to do that by a neural network approach, you first need to select the architecture of the neural network. So how many layers to take, how many neurons in each layer, which activation function. Maybe you don't want to have a fully connected neural network, so you want to pre-select certain entries of these matrices to be equal to 0, and so on. Once you've done that, then you need to learn the affine linear functions, so the weights and the biases. And this you do by an optimization problem. So what you want is that the neural network evaluated in these xi's from here are close to the f of xi's, the labels you actually know. And this closeness is given by a loss function. So for instance, you can take the square loss here. Sometimes you want to also incorporate additional properties of the weights and the biases, and this is done by this regularization term. So maybe you can take a little R1 norm if you aim for sparsity. This optimization problem you then solve typically by what's called stochastic gradient descent. That gives you the affine linear functions, and with this the network, and then you hope that your network approximates on the whole domain. Good, so and from this actually the key mathematical questions arise. So the first area or question complex is expressivity. So this relates to the fact that we need to choose an architecture. So we have to ask how powerful is a certain network architecture? Can it represent the correct functions? So that requires a lot of approximation theory, harmonic analysis, and so on. This is maybe the most explored area so far. Then the learning. So we need to understand the learning algorithm. Does the learning algorithm converge? What are good starting values for it? So that requires a lot of differential geometry, optimal control, optimization. Then generalization. So we train our network on our training data. How does it perform on test data, on other data? Which impact has the depth maybe of the neural network? So that requires a lot of learning theory, statistical learning theory. And these three directions are exactly the three components of the error of a statistical learning problem, namely the approximation error, the error which comes from the algorithmic realization, and then the sampling error. And then there's another area, which is also, I think, very interesting, which is a bit apart from those. And this takes a different perspective. It takes this perspective that I already have a trained neural network, and I want to understand how it reaches decisions, how it operates. Now that's the area of interpretability or explainability, which usually uses information theory, uncertainty quantifications, tools like this. And before I want to delve now into certain of these directions, I would also like to tell you how I actually came to this area, because I mean, I'm not working on neural networks for my whole life. So I changed my research somehow 4 or 5 years ago. And the way I came to it was seeing the impact of deep learning on mathematics, on mathematical methodologies. And you can see that very clearly. I mean, in the area of inverse problems in imaging sciences, they actually embrace these new methods. Why? Well, because I mean, images typically don't have a rigorous physical model. So there's no model of what a natural image is. And so therefore, that makes it very accessible to techniques, to learning techniques. The area of partial differential equations was a bit slower to embrace these methods, because you can ask, I mean, you have a rigorous physical model, which is actually the PDE. Why do you need neural networks? And so what turned out is that neural networks actually are able to some extent, beat what's called the curse of dimensionality in that area. And so that was very interesting. And because of that, now we see many more papers very quickly coming out. And what you see here, I mean, just tiny piece of papers which come out. It's now a huge literature, which is both in both of those areas. And just to show you why these methods are very interesting, let me just show you very briefly, and then we come to the other topics very briefly, 2 applications which we did. And I think this also shows one particular phenomenon. So computed tomography is a very standard method. A CT scanner computes the Ridon transform, and what it does is basically just in this image, you have a body and you compute line integrals through it. This gives you one slice of the sinogram, and then you rotate. And so this is where you create the sinogram, and from this you want to reconstruct the interior of a body. That becomes really hard if you cannot do the full sweep, the full 180-degree sweep, but only a part of it. So basically, you need to recover this interior just from a chunk of this data. Maybe you don't know this whole part. And so what we did in this respect is, and I think this is maybe a useful general conceptual approach, which might also be useful for other methods, we first used model-based methods as far as they go. So there we used what's called Tikhonov regularization with a sparsity term, using shear. That's actually what Felix already mentioned before. So we used this as far as possible. So we didn't throw everything overboard, which people knew before. And then we used the data-driven methods, so the deep neural network, just for what the other methods cannot achieve. And we combined both. And let me just show you the results, which maybe convinces you to some extent. So if this is my original data, I have a 60-degree missing angle. If I do a crude reconstruction from parts of the sinogram, this is what you get. If you use a very good model-based method, this sparse regularization with shields, you get this, but you see there's a blurry part here and here. Now, if you throw everything overboard, what you know about the physics, and just use a neural network, you get something like this, which is already better. And then if you combine both words in some sense, you get a result of this type. And I think this shows the strength of, let's say, taking the best out of both words. And this is just another application, a very standard one, edge detection, where you also want to detect the direction of the edges, where this is the image. And so this is maybe what a human would find as edges. These are two algorithms, model-based algorithms. And so this is what you can do with, again, a neural network combining with model-based methods where we again use shieldeds as a pre-process. So I think that's a very interesting direction to use deep learning in combination with model-based methods for mathematical methodologies like inverse problems and partial differential equations. But I mean, this certainly also requires to understand how neural networks operate. And if we cannot do that, we also have problems actually driving a theory for those applications. And so this brings us back to mathematics of deep neural networks. So where we already identified V3 and also fourth area. And in some sense, if you talk to people from computer science, they always say, well, I mean, generalizations is kind of the holy grail. And this is also the least explored area, maybe it's also the hardest to some extent. And I would like to now show you first a glimpse of what this area is about, and then also what we could do for a very specific situation. So what I would like to show you is joint work with Ron Levy, who is actually a brilliant postdoc right now in my group. Then, I mean, Michael Bronstein, many of you might know from Imperial College, and two master students, Wei Huang and Lorenzo Gucci from Italy. So what is generalization? I mean, normally, if you view this, as I said, as a statistical learning problem, so what you can observe in a classical problem is the following. If you increase, let's say, the capacity, the number of parameters you can choose, the hypothesis class, then if you train your neural network on training data, the error will go down because you actually have more parameters to choose from, and certainly then you can interpret your data in a much better way. But if you then test it, so this is the generalization, if you now test it on out of sample data, as the capacity increases, then at some point the risk, the error will grow. Why? Well, because you do overfitting. And so this, I mean, here's just a very, let's say, tiny example. If you want to do classification between these two groups, so here your hypothesis class is just too small. If you just have a linear one, this might be an appropriate fitting. But now if you have a huge hypothesis class, then you can do a very, very accurate fitting. But I mean, this way, if you now have another sampling point, you will most likely misclassify it because you overfitted. But for neural networks, something very interesting happened, because then if you get into this overparameterized regime, at some point, the test risk will again go down. And so this is what people call this double descent curve. And there are various attempts now to understand why this actually happens. And so there are very many methods also now being developed to tackle this problem. I mean, maybe older methods are the VC dimension, Rademacher complexity, then there's uniform stability, now the neural tangent kernel, and so on. And so there's a huge list of papers coming out now much more rapidly. And this is certainly incomplete what I show you here. Now, what I would like to discuss is a special case. As I said, in some sense, it's also, yeah, to some extent, a generalization. So I would not like to look at just normal neural networks, but I would now look at graph convolutional neural networks. So these you can view as a generalization of neural networks, because these now operate on graphs. And you can actually view the Euclidean space as a special type of a graph with a very special grid structure. And so these graph convolutional neural networks, so the convolution relates to that the weight matrices act like a convolution. So graph convolutional networks are today used for many applications. For instance, recommender systems, also, well, I mean, very, very timely in some sense, fake news detection, but also in the sciences, for instance, for chemistry, because there you also have also graph structures. Now, graph convolutional neural networks, if you dare think about generalization, you already have a much earlier problem in some sense than what we talked about. So what is the problem which you encounter here? Well, I mean, you will train your graph convolutional networks on, well, graphs. So this is the input. But then, I mean, it can certainly happen that you have a certain phenomenon which different graphs model all. So there are different graphs which model the same phenomenon. But maybe you just train on some of those. But then you certainly would like that if the network now operates on a different graph, which models the same phenomena as the graph it was trained on, that then the repercussion is actually the same. So this is what I say here, graph convolutional networks should generalize to graphs and signals which are unseen in the training data. And so this is the concept of transferability. If two graphs model the same phenomena, then such a graph convolutional network should actually give the same output or have the same repercussion on both graphs. So if you, for instance, have some geometrical object and two graphs are a discretization of it in different ways, then the neural network should act in the same way. So this is one form of generalization which actually doesn't occur if you have Euclidean data. So this is, let's say, generalization which already has to happen at a very early stage. And what I would like to show you is that we can prove actually transferability for spectral graph. Now, concerning convolution, there are actually two approaches you can take. There's the spatial approach and the spectral approach. So for the spatial approach, you let the filter act just on the graph, so in spatial domain in a sense, and basically you slide it around the graph. And the filter will aggregate features, information from the neighbors of that node. Or you can do a spectral approach, so that's spectral filtering, where you use the convolutional theorem. We will go in a bit more detail in a moment, and then we multiply in frequency domain. And there was a common belief that spectral convolutional neural networks do actually not exhibit transferability, and I would like to show you that that's actually not true, so that spectral graph convolutional networks are also in that sense actually very valuable and should be used. Okay, so let's talk a bit about what the spectral filtering is about. So I think most of you all of you, I guess, know about Fourier analysis. One can do Fourier analysis also on graphs. One can define a Laplacian on a graph, and so this you do by taking the degree matrix and the adjacency matrix, the difference, and then you normalize it. That's a normalized graph Laplacian. That's a self-adjoint operator. And again, like with a normal Laplacian, you get eigenvalues which relate to frequencies, and you get eigenvectors which relate to Fourier modes, like in the Euclidean space, where here you have these exponential functions. And in a sense, the graph Laplacian then mimics or obeys the geometry of the graph, so which you kind of see here. So here you see this dumbbell shape, and you see the different eigenvectors here, which kind of obey the geometry. Okay, so now how do you do graph convolutions? So you would apply this, normally this convolution operator, in a sense of where you have the filter here, and then you have here the eigenvectors. And so this way you would let convolution act on a function on the graph. Now, if you would implement this now in your neural network and would implement the convolution that way, you actually encounter a problem, because first of all, you need to compute these eigendecomposition, which is actually very slow if you have a huge graph, like for friendship graphs. And also there's no general first Fourier transform for graphs. So you cannot handle this in a nice way. But you have an even more serious problem, because if you do it this way, it is not transferable. Why? Well, because if you now take two different graphs, then these eigenvectors might differ a lot. But this remains the same. It's just a fixed filter. But then if this differs a lot, I mean, there's no way the graph convolutional network with these convolution operators can have the same repercussion. So we need to do something else, and there we delve a bit into Fourier functional calculus and Fourier functional analysis. So don't worry if you don't know about functional calculus. What this is about is actually a very nice concept. If you have a self-adjoint operator, it allows you to apply a function to it. So let's assume you have a self-adjoint operator, and then you can actually formally define a new operator, which is, in a sense, the function applied to this operator. And so you can have a decomposition formula of this type. You see, you have here the eigenvalues, and now here the eigenvectors, and here the eigenvalues where now you apply this G. And if the G has certain forms, for instance, it's a rational function, then this you can actually compute in a nice way, because then this is just this formula. So you just plug in the T here in your rational function. So now we will apply this to the graph Laplacian. And so this you see here. Yeah, so this is what we saw before, where we encountered these problems. Now we use a different formula for computing the convolutions, or a different approach, let's say. So now we apply a function, and now the function, this function G, is our filter. We apply this to the graph Laplacian. And so we already saw the right-hand side there. So this is the way we apply now convolution. So that's our filtering operation in the graph. Why is this good? Well, I mean, it solves our instability problem, because now if, let's say, you have two different graphs, then for the associated graph Laplacians, the eigenvectors might differ, but this differs as well. Yeah, so the problem was that this remained fixed. So now this differs, and this compensates basically for the change in here. So this makes this much more stable to perturbations of the graph. Also, it solves the computational problem, because now here, remember, I needed to compute the eigendecomposition, but that I don't need to do anymore if this is a rational filter, because then I can compute this side directly. I don't need to compute the eigendecomposition. Okay, so this is now the type of filtering I apply. Yeah, remember, I mean, we take the graph Laplacian, and then the G acting on that is the filter. Okay, so now our task is we first actually need to define what we mean that two graphs model the same phenomena. Now remember, our task was we have two graphs which model the same phenomena, and then we want to check and analyze whether, if we apply now a graph convolutional network to it, whether it has the same repercussion. But first we need to understand and give a precise meaning for the fact that two graphs model the same phenomena. And that we do in the following way. So remember, I mean, a weighted graph is, I have points, and then I have basically the weight, which gives me the strength between those points. There's a different concept, which is kind of similar. And that's the concept of a metric space. A metric space has also points, in a sense, and distances between points. And now the way we view it is, we say that two graphs represent the same phenomena if there's a metric space above them, and they are the discretization of the same metric space. And so you can imagine that if, let's say, I have a distance in my metric space and the distance grows, that corresponds to the fact that my weights become smaller. Yeah, so basically I embed the graphs in a metric space, and if this is possible, then I say they represent the same phenomena, and that also gives me a means via this metric space to move from one to the other. Okay, so now I need to compare the repercussion of a filter on two different graphs. And this hopefully explains also what will happen and what we will do. So now assume I have these two graphs, and they come from the same metric space. So now I take a generic signal on the metric space, which I call F. Okay, so now I want to compare the repercussion. So now I first sample, I bring it down on the graphs. With a sampling operator, I bring it on the first graph, I bring it down on the second graph. Now I apply my filter. And remember, the filter was, I apply a function to my graph Laplacian. So I apply the function, the same filter, but to the different graph Laplacians, because these have different graph Laplacians. And then I want to compare. So now what I need to do is I need to bring it back. I need to bring it back to the metric space. So I bring it back with a reconstruction operator, and then I can compare. Yeah, so I have my function on the metric space, I bring it down on the graph, I apply the filter, and then I bring it back, and then I can compare it. Okay. So that I would like to estimate now. So this field with a bit more life. I have my analog domain, so my metric space. I have a Laplacian there as well. I have my digital domains, my graphs with the graph Laplacian. On my metric space, I have band-limited spaces, Pauli-Wiener spaces, which correspond to this. And from these Pauli-Wiener space, so that's a Pauli-Wiener space according to lambda, band lambda, I have an operator, the sampling operator, which brings it down to the graph. And then I have another operator which brings it back to my manifold. And so this P of lambda is just the Pauli-Wiener, the projection. It's an abbreviation for the projection. Okay. So now, yeah, so that looks, I mean, like a lot of math, but let's look at it, what it actually says. So please just take a look at this green part here. So what it says is, so this is the transferability of the filter. And if I compare it from the digital to the continuous domain, so you see what happens. I have an element of my Pauli-Wiener space. I bring it down on the graph. I apply my filter, and I bring it back. And I compare it to if I adjust to the same on the metric space. And I can estimate it by these two terms. So the first term is, as it says here, the transferability of my graph Laplacian. Yeah, so you see what happens here is the filter is just basically the identity, and I bring my function on the graph and I apply graph Laplacian, and I bring it basically back and compare it to what happens with the Laplacian on the metric space. The second term is what one might call the consistency error. You see, it checks how close the sampling and reconstruction procedure is to being the identity. Okay, so that's one part. So now I compared, if I just use, let's say, one filter with, sorry, if I compare what happens now for one graph with what happens in the metric space, but I would like to compare what happens with two different graphs. And basically, we also use the previous result, as you can imagine, and not going through all the details where you have now two different graphs, you have two different graph Laplacians. You have one graph convolutional neural network with ReLU filters. And then this is the error which you need to monitor. So you have your element in your Pauli-Wiener space, you bring it on the first graph, you pass it through the neural network through all the layers, you bring it back to the metric space, and you do the same also for the other graph. And you get a very nice estimate. So you estimate it by the number of layers, the D, and if I go back, so this was a constant depending on the filters and the dimension of the Pauli-Wiener space, and then this delta corresponds to the estimates we had before, so what happens in each of the layers. So that way, I mean, now you can keep this generalization error under control. And so in a sense, I mean, this is one part of transferability. One can in general look at transferability from two different ways. I mean, there is what's called the concept-based transferability. This is if your training data set has different types of graphs, and the neural network, in some sense, that way learns to transfer maybe also to another graph. Then there's the principal transferability. If you just maybe have one graph in your training data set, and then there's a built-in capability of graph convolutional networks to transfer. And this is actually what we analyzed now and for which we get a very precise bound. So for spectral graph convolutional networks, this actually already works, and we can bound this. And this is then some, let's say, additional concept which certainly makes it even better. And so let me just show you, to finish this part, one numerical example where you can actually now isolate principal transferability from concept-based transferability. So we have two different convolutional graph neural networks where we use 1 spectral filters for this Cayley one and spatial filters for this monad. And what you see here, so here you have an image and you can take different resolutions, and these are the different graphs which mimic the same phenomena. But the neural network just saw one resolution. And you see that here with the spectral graph convolutional network, the accuracy is actually much better than for the spatial. Okay, so that was one glimpse into generalization. And as I said, I mean, it's a huge area. It's tremendously important. It's also very exciting because there are a lot of people now jumping in with different new methods and new ideas. And what I showed you was one specific problem in the setting of graph convolutional networks, which actually doesn't appear even in the Euclidean space. But then you can say, well, I mean, right now people are still working on these parts, but we already have neural networks and they are there. So we also need to analyze them. So we need to ask the question now, if we have a neural network and maybe we don't have any error bounds for it or anything, it's just there, we got it from wherever we have it. Can we analyze it? Can we understand how it actually reaches decisions, which is really critical in sensitive applications? And that's the area of interpretability. And so this asks the question, I have a trained neural network. I don't know how it got it. I maybe don't even know the training data. Can I understand how it operates? And you can imagine that this is actually crucial. So for instance, if you apply for a job, it's rejected. And then you ask why, but maybe the rejection was done by a neural network-based algorithm. So then the person who actually sent the rejection has to give you a reason for that. So he or she needs to ask the neural network-based algorithm, why was this decision made? And so in a sense, the vision for the future is to then, I mean, get a decision or an explanation for the decision out of the neural network, which is indistinguishable from a human being. We are very far from that, but I mean, this is certainly one goal for the future. And there are various approaches from various different directions, gradient-based approaches, backwards propagation-based methods, and so on. What I would like to show you is what we think is also a very mathematically based approach using information theory. So what typically people do these days is, I mean, looking at images, and then you get a classification decision, and then you would like to know how important is each pixel for this decision. So imagine you have, for instance, classification of handwritten digits. Let's say these 3, and the neural network classified it as a 3. Then these pixels, these red ones, are actually quite crucial for the decision. Why? Because they indicate that that's actually a 3 and not an 8, because that's actually open here. But these parts, these blue parts, are actually not that great because it seems to close. And so this counts against the decision. For an 8, it's a bit different. So there, I mean, these areas, these pixels are speaking against the decision, whereas the others speak for the decision. So basically, people aim for putting a heat map on the input data, which tells you for each pixel how important it is. And what I'd like to show you is now, and people call this a relevance map. So what I would like to show you now is a mathematical definition of relevance by information theory. This actually allows us to formulate this interpretability problem as an optimization problem, which also opens it to a very rigorous mathematical analysis. We also get a canonical framework for comparison, and we can then also extend it to other modalities, not only to images, but also to audio data and very much whatever you can think of. Okay. And so the first part is joint work with Jan McDonald, Stefan Bellchen, and Sascha Hauch, so 2 PhD students and a master student from TU Berlin. Okay, so this is the problem. We have a classification function, maybe on the domain 0, 1 to D. And we have an input signal. So let's assume it's usually always images. We have our original image X. And now what we would like to determine is which are the most relevant pixels. So that will be a subset of my pixel space. So I have certain pixels, and these I want to label as being relevant for the decision. So that I call S now. S will be always the relevant pixels. And the complement of this shall be then non-relevant. Okay, so now I want to determine what is actually a good meaning for these relevant. What does it mean precisely? And there I will borrow from rate distortion theory. So what is rate distortion theory about? Now, rate distortion theory is always, I have a sender, Alice usually, she wants to send a message to Bob. She doesn't want to send the complete message, just a part of it. That's the rate. And then Bob receives this message, so not the complete message. So there's an error which happens. And this error is the distortion. So now we want to phrase it in this framework. So let's assume I have my neural network, phi. Alice has it and Bob has it. And I have an image, and it's classified originally as a monkey. Now Alice would like to send pixels to Bob, and she wants to send the relevant pixels to Bob, those pixels which are relevant for the decision, because Bob in the end should get the same decision. So she sends a couple of pixels to Bob, this partial image. Now Bob has to do something because he cannot let his network operate on this part image. It operates only on the complete image. So he needs to fill it with something, and so maybe in some sense the least disturbing is to fill it randomly. And then this random completion he puts in his neural network, and he gets a decision out, and hopefully it's the same decision as also Alice got. Yeah, so now, I mean, the rate is how many pixels you send, and the distortion is the error which you make. So, and this tells you how important actually these pixels really were. Okay, so now we can phrase this all mathematically. So I have my noise with which I would like to obfuscate my partial image. And this vector y, which Bob assembles, comes partly on S from X, on the original image, and on the complement, it's noise. Okay, so now this we already saw before. So now the distortion is the difference between phi of x and phi of y squared and the expected value of it. And now I can ask the question, I want that the error, the distortion is less than some epsilon. How small can I actually choose my relevant pixels so that this is still, so that the distortion is still under control? I would like to find the smallest set of pixels, so a very concise, let's say, explanation, so that the distortion is still under control. So that way, that you can actually see as a definition of a relevance map. Unfortunately, as many of you can imagine, to compute this is actually very hard. In fact, even more than NP hard. So, as if you're working in the area of compressed sensing, you know that then in this case you relax. So we need to relax this problem. And that leads to what we call rate-distortion explanation. So here, what we just discussed was only a 0-1 decision. Either pixel is relevant or it's not relevant. Now we relax it. So for each pixel, you give it a relevance value between 0 and 1, not just 1 or 0. Now, so that's a special case. You can also obfuscate in a similar way. The distortion is defined in exactly the same way. Instead of the rate, now you take the little r1 norm. This leads to an optimization problem, because now you can minimize the distortion and the rate, now with a regularization parameter, lambda, subject to S being in this, so this box is constrained. Okay, so now let's look at some examples for this. Let's say I have a neural network, which is actually really good. It has a test accuracy of 99.1%, and it classifies handwritten digits. And I want to analyze it. I want to analyze why, for instance, something was classified as a 6. So what I'll do then is I use this Rate-Distortion Explanation. And here are also a lot of other different algorithms, Deep Taylor, Lime, and so on. And all of these give different explanations. You see, all of these are relevance maps. You see ours, what we think is nice here is that here indeed, I mean, this part of the 6 is indicated, which indicates that it's really important that this is not closed. But now you can say, okay, well, I mean, you see all these images, they look nice, but how to compare? No? Otherwise, it's just visual comparison. And so there you can actually now compare it in the following way. You can compare how many relevant pixels you indicate, so to have a concise explanation, versus the error which you make. And so here you see that with very few pixels, you still get you get a small distortion. Yeah, so here nicely, I mean, the curves for our approach actually decays the fastest. Yeah, so with very few pixels, you already get a very small error. Yeah, so in a sense, you have a very concise explanation. Okay, so that's actually a nice approach, but there's still a lot of room for improvement, and so this I would like to just in the last minutes tell you about that. Now it's very new work, and that's joint work with again Ron Levy, whom you already saw before, then one of my master students, Cosmos Hayes, then Joan Bruno, I think everybody knows, and one of his PhD students, John Bresnik. And so the problems, or some problems which one can ask and which one need to think about are the following. So first of all, you see you obfuscate here with random noise. But then the question is, does it really give meaningful information about why the neural network made its decisions? Because that's a very artificial image. Wouldn't it be much better to get something which is close to the data distribution in a sense, which gives you actually much more information on how relevant these pixels really are? The other is that the explanations are, as we said, pixel-based. So now if you have different modalities like audio data, other data, I mean, is this sufficient? Can you actually also expand it to other types of modalities? And so the goal is also to take the conditional data distribution somehow into account and get obfuscations which are actually much more meaningful, to extend the algorithm that way, and also to see how we can actually handle other modalities and other data modalities. So this is recalled from what we already saw before. So this was the distortion, which we considered before, where the Y now followed some distribution. And so the distribution was always that I take, if I just have a 0-1 decision, these pixels, and I obfuscate this by random noise. So how do I bring the conditional data distribution in? Well, I mean, what I can do there, for instance, and this was one idea suggested by Shan and collaborators, is the following. We can train an in-painting neural network, so that if I now have parts of the image and I'm in-painting it, that one has a critique, very smart critique, has problem to decide whether this obfuscation, yeah, so you see now we do the obfuscation not with random noise, but what we get out of the web generative network, of the in-painting network, whether this came from the data distribution or not. So in that sense, I mean, just think of it that way, we obfuscate it in such a way that it comes from the data distribution, the underlying data distribution. So here we assume we actually know the data distribution to some extent. And so then we can now set up a very general problem. So we can ask, so what we would like is we would like to minimize this distortion and also the L1 norm, and the Y is now generated by a GAN, by an in-painting network. This is the obfuscation which we pursue. And the advantage of this is that we can apply this now, and I will show you this very briefly in the last 2 minutes, to applications, to various other modalities, for instance, audio data. And we can also combine this with a transform. So for instance, you can apply Gabor transform, other transforms, and then apply this approach in the feature domain. And for instance, as applications, we looked at audio processing. So there's a data set and a neural network which we took, which classified instruments. And so for instance, the query, the question we asked there, which you can answer with this approach, is to which extent does the neural network in its decision relies on either the magnitude or the phase, and not unexpectedly, the phase is certainly the much more important feature in general for the decision. And a very different application came from telecommunication. So there we ask a very different, so that's a very different scenario. So we have some work there with also colleagues from electric engineering, and the question is the following. So you have a transmitter position, you have buildings, and you have sample values. And what you would like is, so the sample values are maybe people with cell phones. And what you would like to know is, you would like to know the strength of the signal, if this is my transmitter, in all points. So what you want to compute is this black and white image which you see underlying. Yeah, so for each position, you want to compute the signal strength. Then you can ask, for instance, now, I mean, what the neural network computed was this dark area, although there is actually no building. And so one can ask, why was it actually computed at this point? So it's a very different query from before. And again, with this approach, we could actually explain this and say, well, I mean, because of exactly those measurements, because they have here a different color in some sense, I mean, this was in-painted this way, and actually what this shows was that there, in the original map, a building was missing. Okay, so I think my time is up, so let me finish with some conclusions. So what I hope I showed you is that neural networks and mathematics of neural networks is a very exciting area. They show really impressive performance for classical mathematical methods. That actually also how I came to this area, in particular inverse problems and partial differential equations. There are now very exciting theoretical questions to also explain those applications, and one can group them in this area of expressivity, learning, generalization, and interpretability. Then we delved a bit deeper into generalization. I showed you one part of generalization, which actually appears for the application of graph convolutional networks, is transferability. And I showed you that we could actually solve this and estimate how good spectral graph convolutional networks transfer or transferable. And then if all those fail, we go to the area of interpretability, which asks a different question. Given a network, how does it operate? And I showed you one way to actually give a bit more, let's say, mathematical notion of it, drive a mathematical or also information theoretic theory there, and get to a very general and flexibility approach. And with this, I'd like to conclude and Thank you very much for your attention.
Thanks a lot for your talk. Any questions from any of the panelists, or if any other attendees want to put questions into the Q&A, the panelists will try to answer them going forward.
So while people are still typing questions, let's maybe take some questions that were asked during the talk, and in particular,